Well, thanks for making it back from lunch. So I'm glad we made it back for the last lecture of today, before we let you into your practical sessions. I'm changing, obviously, tact quite a lot here. The three speakers of the morning did such a great job at giving us the very large-scale overview of the Southern Ocean, the processes, the main processes that are at play, and of course how it's changing in our current climate. And I'm being asked to really focus much more on the fine-scale Southern Ocean. And this is the kind of image that I think is summarizing many aspects of what I would like to try and cover today and tomorrow of the fine scale. I'm not sure if any of you recognize this piece of land. Any hands up? Okay, then we're going to pretend it's the Antarctic Peninsula. And what we see is this traces. I hope that the oceanographers start to look more at, these kind of patterns on the slide and realize that this is sea ice that's being stirred around. It is acting as an ocean tracer for the fine scale. And so we have this wonderful natural tracer off the coast of Antarctic Peninsula, that really tells us something about what's going on in the ocean here. And we can see, these eddies which are occurring at the 30-kilometer scale. So this is a MODIS image. It's a satellite measurement that's actually got a resolution in this color band. This is sort of near visible, of roughly 300 to 400 meters. So each pixel is about 300-400 meters. And it obviously picks out these sort of more, at these latitudes, 70 degrees, these are more mesoscale features, 30 kilometers. And then also we can go, another order of magnitude smaller to 3-kilometer little eddies that are kind of being pinched off the mesoscale and sort of connected to the edges of these mesoscale eddies. And then we could also go down even further, and we can see these little strands that are only maybe 2 or 3 pixels of the satellite image wide. And these are roughly another order of magnitude smaller, and we're going to sort of 300 meters. So the ocean is full of these vortices and circulation patterns that we haven't really been able to observe until recently. We've relied on a lot of high-resolution modeling simulations to understand how these processes occur, because we can model, especially the last 5-10 years, down to hundreds of meters or a few kilometers. But observations have been very scarce, and we've been reliant on these remote sensing observations to kind of show us that something's going on here at the fine-scale ocean. So, so I'm Sebastian, Seb. People call me Seb. I might look Swedish, but I'm not at all Swedish. I'm South African. So, I spent before Sweden, sort of 16 years in Cape Town at CSIR. It's a SOCO. And I think I read a bio that there are maybe a few South Africans in the crowd. Yeah, there's one waving. Any other South Africans? Three South Africans. Sanibonani. It's really nice to have some South Africans here. And then about 8 years ago, I moved to take a new position at the University of Gothenburg in Sweden. And so I regard myself as an observationalist, really mostly focused in the Southern Ocean. I really am interested in the fine-scale ocean circulation, which is something I'm going to try and introduce today and tomorrow. And I really like to use autonomous platforms like ocean gliders and autonomous surface vehicles that stay on the surface remotely, and we pilot them around to collect observations for us. So I'm going to try bring that in. One thing I did want to mention, and I'm sorry it sounds quite blunt, but it's incredible to see the diversity in the summer school. I actually did a little count during. Sorry, Sarah, it was your talk, but I was very interested in your talk. But during Sarah's talk, I did a little count through the Facebook page, and I noticed, I think, if I counted very quickly, there's 32 women, females. I'm sorry if you don't identify as female or male, but generally speaking, 32 females and about 16 men. And I think that sorry to be blunt about this, but it is really interesting to see that dynamic and diversity is really coming through in a field like oceanography. So I hope in 5 years, or hopefully less, maybe some of you are, in these faculty positions and changing oceanography at the global scale. Anyway, I'm in Sweden. Yes, we have this cheesy group that's called Polar Gliders, but we love it, and it's really that we do mostly polar oceanography, focus on Southern Ocean, and we like to use these autonomous platforms. I was thinking if Matt had to call his group, would it be like Polar Models or something like that? Would be terrible. Don't do that. Okay, so this thing, I think I have to point to it. Right, so I really want to cover today a little bit about the Southern Ocean mixed layer and sort of simple dynamics. Obviously, diverse background here, so I'm trying to cover the interests of many of you, if possible. Tomorrow, I really get much more into fine-scale horizontal circulation, and what I mean by that is a little bit more about the submesoscale circulation. And through the 2 days, I hope to try and connect these processes to the top and boundary fluxes. And what I mean by that is that I want to show that these processes are important to things like air-sea fluxes on the surface of heat and carbon, or the bottom boundary fluxes like ventilation of heat or carbon or nutrients or whatever it might be into the ocean interior. Maybe I'll do a bad job, but I'll try and bring in those examples. And these are actually very few examples in the observational field because we're just starting to make these observations. So it's quite at the sort of edge of what we're trying to do in research for the whole community. And I try and think of some theory, bring in some observations and modeling, and then of course the technologies through some of the autonomous platforms. Okay, so this topic is really complex in the Southern Ocean. Here's a bit of a plug to advertise a really interesting chapter in a textbook that Sarah led with some of us helping her to show all these different processes that occur in the Southern Ocean. This is in the textbook Ocean Mixing by Alberto Garabato and Mike Meredith. I can really recommend it. I love reading it, and then I noticed that there's such a high correlation between opening the book and someone coming to my door to interrupt me. So I haven't really got past like chapter half or something, or the first chapter, but I know it's good. And this chapter really deals with the Southern Ocean. It's very complicated because we have these various processes on the surface and in the lower marine boundary layer interacting together at various scales. And here I'm talking about hundreds of meters, like Langmuir cells, wave wind interactions that generate a secondary circulation of only hundreds of meters, to these submesoscales in a few kilometers, to these big storms, like thousands of kilometer size storms rolling over at high frequency over the Southern Ocean. We know it's changing. We had, that was really done very nicely this morning. I'm not going to talk a lot about how it's changing, but we do know that the surface layers are also really changing. The northern latitudes of the ACC are really warming. There's high confidence about that. The southern ACC regions or southern Ocean is freshening and cooling, and there's also high confidence in that. So it's a really complex area, and it's also changing in our current climate. Now, what is why is this such an issue? Why do we care about the fine scale? And so here I've got just a representation of an Earth system model that, of course, we really rely on these things to understand how our Earth and climate is going to change in the coming century. And these climate models have a resolution order, 100 kilometers. They can resolve processes sort of, maybe 30 to 100 kilometers in size. And so that's pretty coarse, especially if you're thinking about the fine scale. And I really love this analysis that was done by Baylor Fox Kemper, who looked at Moore's law. And that's how long it takes from now into 50 years, how our growing capability will be for microchip processing. So how we can start to increase the resolution of our models in time as a function of our improvement in computation. And he put all the climate models together. You know, here's the intercomparison experiments. Here's AR5, AR6. And here is the spatial resolution with time. So we're getting smaller and smaller scale. And, you know, we're kind of in the submesoscale range. And here's mesoscale. And right now, we're just sort of above the mesoscale. We're heading, you know, into a better resolution space in time. But if you want to understand the submesoscale and the fine-scale ocean, we're going to have to wait till about like 2060 or 2080, so a lifetime away. So that's a really big problem. And so here is a nice cartoon made by someone I work very closely with. He's a researcher in our group, Marcel Duplessis. Some of you might know him for flux work and SoFlux. In that community. Anyway, he made this nice cartoon for a project proposal, and you see the Southern Ocean is filled with these little eddies. This is conceptual. There's the sea ice interacting with the surface ocean, and these processes are happening at 1 to 10 kilometers. So how do we get to understand this knowledge in the climate model where we're predicting our climate for 100 years? So this is really a difficult topic, and I hope that maybe by tomorrow we'll start kind of talking a little bit about how we're getting there. Okay, so now we're just going to, you know, take a step back and go more simply into what is the surface mixed layer. I know not all of you understand the surface mixed layer. So why is it important to the Earth system? Why do we care about these couple of tens to hundreds of meters of the surface ocean? Well, I like to think of it in terms of our seasonal temperature range at any given year. So this is the global view of how the temperature would change at the surface over an annual cycle. This was 2016. And you can see that, well, any land near the ocean sort of smudges away, gets sort of lost in these blues where the temperature range is really small. And when you're in the interior continents, like, you know, Russia here, in the interior Asia or North America, or in the high latitudes, the temperature range is very high. And this is really because of the ocean. The ocean is providing a maritime climate and situation. It's not only the ocean, there's water vapor here as well in the air. But let's just think of it as only an ocean view. The ocean is kind of putting this pattern into place. And that is because the ocean is such an enormous ability to take on energy and heat. Its heat capacity is huge compared to the atmosphere. And a lot of this is occurring in that mixed layer. The mixed layer of the ocean is buffering the seasonal temperature changes that we see across the Earth. So without that mixed layer, or without the ocean, of course, you know, uninhabitable and extremely hot and then cold and not a great place to live. So the amount of energy that would require, for example, to give you a perspective of this heat capacity, to warm a mixed layer, an average global mixed layer by 1 degree Celsius would have to take all the energy in the atmosphere times 30 and put it in the ocean. So just 1 degree Celsius is about 30 amounts of energy in the entire atmosphere. So it's really very, very important on a climate scale. And then, of course, for the biologists in the room, well, it's also really important for biology. And here we have these monthly climatologies of chlorophyll from satellite color, and we can see these beautiful blooms over the Southern Ocean. I know you've seen this many times before, but you know, this is really regulated by the mixed layer. The mixed layer is controlling the amount of light and nutrients that's available for these phytoplankton to grow. And even though we have lots of nutrients there, what we're missing is this micronutrient iron, and that's being tapped into with the deep mixed layers and then shoaled to be a nice light environment and allowing for these phytoplankton blooms to really get very excited in the spring, summer months over the Southern Ocean and provide a critical link to the ecosystems that live there. All right, so this is a typical profile you would have in the Southern Ocean. Just going back down to basics, this would be just temperature. So we see a nice thermocline at depth. And we can see that generally the top layer, this is 100 meters deep, this mixed layer is homogeneous. The temperature, and you could imagine salinity and other things are not changing with depth. And so to determine where this mixed layer is, we're using these very simple criteria, these thresholds, which look at a jump in temperature or density at a given depth. And we typically use this one of change in density of 0.03 kilograms per meter cubed from a reference level higher up in the water column. So that's how we kind of determine the mixed layer. And these mixed layers are impacted by several aspects at the surface. And Sarah has alluded to a lot of this in her talk, and I'm sure she will go into this a lot more detail tomorrow when she's dealing with fluxes. But firstly, the mixed layer is really adjusted by the balance between wind and buoyancy. I mean, just from a very simplified view. So the wind, of course, causes a lot of stress on the surface. This can cause active mixing of the surface mixed layer. It generates waves that break. So we add turbulence and bubbles to the mixed layer, which also increase mixing. Matt spoke, it wasn't Matt, it was David who spoke about the Ekman spirals that are generated by the wind stress. And these Ekman spirals, here's a typical view of an Ekman spiral that we might see in the surface ocean. And they're adding a lot of shear stresses to the surface mixed layer. Not only is the velocity in Ekman layers changing as a function of depth, but it's also changing the direction at which that flow is occurring. So we're kind of adding shear stresses in the mixed layer that can create mixing and mix and deepen the mixed layer. And there are other things like Langmuir circulations, which I don't think we're going to get into, but we could talk about. And this is really something that has been revived in the research space, is understanding the impact of Langmuir cells and circulation in Southern Ocean mixing, where waves and winds are very strong. Okay, so some of you, who's been to sea? Who's been to the Southern Ocean? Okay, a lot. Okay, so I don't need to really explain this one, but you're standing on the deck and you can really imagine these incredible winds of the Southern Ocean whipping up these waves and creating a lot of turbulence that deepen the mixed layer. Now, this is a view of what those winds look like, typically over the South Atlantic Ocean. So we have these incredibly strong, I mean, here we're talking about category 1, 2 in the deep reds, stormed forcing over the Southern Ocean. And I guess what I want for you to take away from this image is think about the frequency at which the storm forcing changes. And I'm trying to take you back to the fine scale ocean. These storms may have a very long temporal mean imprint on the Southern Ocean, but when you're able to view them, day to day or hour to hour, they change very rapidly and they have high frequency variability. So if you're just a point here, these are some glider deployment locations. So let's say you're a glider here, and you're sitting on the surface. You can see what you feel in a given week. Pretty calm conditions, and then bam, Hurricane 1 kind of intensity storm hits you. And the surface forcing is really amplified and strengthened, and these have implications for the surface heat fluxes that Sarah will probably mention tomorrow. So there is a very strong spatial and temporal component to the variability that the Southern Ocean feels, which is something to take home. Right, so these are all these different processes that the wind is doing to deepen the mixed layer. I spoke about the Ekman spiral, the breaking waves, the Langmuir cells. And so I'll ask you, why doesn't the Southern Ocean mixed layer just deepen? Why doesn't the global ocean mixed layer just deepen down to the bottom? Why wouldn't that occur? Any guesses? It's easy. I promise you it's easy. It's not a trick question. A loss of energy. Okay, sort of. What do you mean by that? You mean we've got decaying wind stress or stresses with depth. Right, so the Ekman spiral eventually reaches 100 meters and no more. Okay, so that's what you mean. Yeah, so you're partially right. Yeah. Yeah, okay. Leah? Yeah. That's right. So all kind of right, and then Leah put the cherry on the top. because we have processes that are fighting against the stresses from wind and mixing processes through the input of buoyancy. So it's not just wind but we also have buoyancy in the form of surface heating. And the answer was always in front of you, right over here, just outside the circle, where the sun is warming the surface layers, you're warming the water, you're increasing the buoyancy, and so you're adding stratification to the surface layer of the ocean. The same can be said for adding precipitation and fresh water. And of course, in the Southern Ocean, there's a huge other domain, which is the sea ice and the land ice freshwater processes that enter the Southern Ocean. Okay, so buoyancy. We don't really need to go again, we've just really spoken about it, but this heat or fresh water, when they increase, you add buoyancy, so they stabilize the ocean. We call it stably stratified. It's basically how an ocean profile would organize if you just let it to rest. It would become stably stratified. But of course, you can also remove buoyancy. You can take out heat. You can create sea ice and increase brine. And so you can take away buoyancy and deepen the mixed layer as well and create an unstably stratified ocean. Okay, here's a nice example in the recent research where we think about this buoyancy in terms of rainfall. And there's actually been a lot of news about atmospheric rivers in the last few years. California. Tell me about it, Sarah. I mean, you guys are, atmospheric rivers are the big thing. Yeah, exactly. What's it called? Pineapple something. Pineapple.
It used to be called
Pineapple Express. It's not very good in the scientific literature to say Pineapple Express arrived at the coast. But indeed, we have these atmospheric rivers, and an atmospheric river is really, as it describes, it's a river that's, flying over us, carrying a huge amount of water, like in, a bit of an Amazon, in terms of water vapor content that these atmospheric rivers transport precipitation over the sea and over the land. And this image here is some reanalysis product showing rainfall and water vapor in the atmosphere. And you can see here over the South Atlantic Ocean, what actually happens is that these mid-latitude storms that are moving over the Southern Ocean here link up these atmospheric circulations, meet in the upper atmosphere with the subtropical, tropical atmospheric circulations. So in this case, we're taking direct water vapor that's come off the Amazonian rainforest. It's circulating in the subtropics and is connecting to a mid-latitude cyclone, and it's creating a channel by which we can bring an entire river or multiple rivers of water vapor into the atmospheric circulation over the Southern Ocean. And what it does is these red colors show the precipitation associated with that. So they strongly enhance the storms in the Southern Ocean in terms of precipitation and energy. And we deployed some of these autonomous platforms. So here we put one of these wave gliders at that star. So it's somewhere in the sort of 45 degrees, actually this one's further south, 54 degrees south or so. And we put these wave gliders there, these autonomous surface vehicles, and I know many of you don't know all these instruments. So this is a wave glider that has this umbilical cable on the surface down to this sort of Venetian blind kind of apparatus at depth. And what happens is it's wave powered. So a wave moves over this wave glider, and we have lots of waves in the Southern Ocean, luckily. And the surface wave amplitude is higher than at depth. And so the surface platform gets displaced much more than the one that's 8 meters below it, this platform. And that creates a lot of torque along this cable, along this umbilical. And it pulls this instrument up and then releases it down at the back of the wave. And the Venetian blinds close out and push the whole wave glider forward. So in fact, this apparatus at 8 meters deep is pulling the surface vehicle around with it. And in a place like the Southern Ocean where there's lots of waves, we can keep these gliders out there for months. And in this case, this glider was deployed for about 5 months, measuring things like surface heat fluxes, wind speed. Oh, well, actually, I think I just showed that. Yeah, so this is just 1 day of information. Here we've got wind speed from the glider. We've got precipitation from reanalysis products, so how much rainfall. Here we've got salinity, because the glider is carrying a CTD, this wave glider. And what it shows is that one of these atmospheric rivers links up at this location, passes over the glider. We have this very dramatic change in wind speeds. There's rainfall. And then this leads to a dramatic drop in surface salinity. And in fact, the contribution of this surface precipitation to buoyancy, to surface buoyancy, is about 2 times what you would get from solar radiation. And over a seasonal cycle, this equates to about 10% of the surface buoyancy over the summer in the South Atlantic. So these atmospheric forcings that are very rapid and can bring moisture all the way from the Amazon into the Southern Ocean are really important for understanding the surface mixed layer. Okay, so it's really complex, think of all these processes in the Southern Ocean. What I mean by that is that all these processes that are made for the global ocean are heightened in the Southern Ocean. We have bigger waves, we have stronger winds, we have large Langmuir cells, etc. We have pretty good precipitation as well. And hopefully tomorrow we're going to cover a little bit more about what about also the fine scale processes, the 3-dimensional circulations that occur in this mixed layer that adds another level of complexity. Okay, so here's a view of the surface mixed layer over the global ocean, and you can see that here in the austral summer, the Southern Ocean has these pretty shallow mixed layers. Pretty shallow, I mean, they're still 60 to 80 meters deep, so it's pretty deep, but generally quite shallow. We've got strong solar radiation that's adding a lot of buoyancy to the surface layer. We've got sea ice melt that's freshening and being advected north and adding more buoyancy that allows mixed layers to not deepen as much as they would. And then you go to winter, austral winter here, and really we see these dramatic increases in mixed layer depth. These deep reds here are going off the chart, and there are many mixed layers here that are in the order of 4 to 5 to 600 meters deep. So really quite dramatic. And there is also spatial and temporal heterogeneities, and hopefully tomorrow we'll talk about that a bit more. That's being influenced by the submesoscale and mesoscale ocean. So stratification, we spoke about the mixed layer itself, but it's set by how stratified the ocean is. And one of the metrics that we really use, which some of you may not have heard, is this Brunfeishaler frequency. It's about how stratified the ocean is, or at least at the base of the mixed layer, how much energy do we need to break through this mixed layer to deepen it. And we can measure this stratification as a function of just really the change in density with depth. And it's basically how much a parcel will oscillate when it's displaced in a statically stable environment. So that's why it's this frequency. It's given as per seconds. Right, I do have a lab experiment which will kind of explain to you what Brunfeishaler frequency is. I quite like this one. I'm going to jump a bit. Where's this? Here. Okay, so here we have a bottle. This bottle is neutrally buoyant. It does, when you put it in its environment, it doesn't, it's neutrally buoyant to that given environment. It's the same buoyancy inside the bottle than it is in its environment. So they take this bottle and they oscillate it in a stratified fluid. So it means that above the bottle, it's less dense, and below the bottle, it's more dense, just like the average ocean would look like. And this bottle that's neutrally buoyant doesn't want to be in this nice light ocean environment, so it sinks. And then it overshoots its neutral buoyancy, and it goes past that until it's in this much heavier water, and now it's much lighter than that water, and it shoots back up again. And so we get this oscillatory movement of this, in this lab experiment, of this bottle oscillating in a stratified fluid. And that's why we get this frequency. And we're measuring the frequency at which this bottle oscillates. And that's essentially what n squared is. That's why we measure it as a frequency. So you can think of the Southern Ocean water parcel and taking a parcel of water at the surface and pushing it down. What might it do? And that frequency is really determining the strength of stratification. Okay, so now let's look at a few observations. So here we go into the Southern Ocean. Now this was done in my years when we were in South Africa. We started to deploy these gliders in the subantarctic and subpolar Southern Ocean in 2012. So here's on the SA Gullis. This is a wonderful ice-breaking platform vessel from the South African National Antarctic Program. And we take these gliders, and in these, not really nice conditions, we sort of gently throw them off the back and hope that they're going to survive for several months. And what we did is we did that for many years in a row. For about 6 or 7 years, I think it was 7 years, we deployed these gliders in various positions in the subantarctic and subpolar Southern Ocean for many months at a time. So about 5 to 7 months, these gliders would be doing their thing while we're piloting them around, but they have to survive out there, because if they don't, we're not coming back to get them for another 6 or so months. So they have to survive, and they have these wonderful lithium primary batteries on them that make them last that long. And they require very little energy to fly through the ocean, because they're changing their buoyancy by pumping oil inside and outside of its chamber. And that's how they fly through the ocean. They're not using an active propeller, which uses a lot of energy. So if you look at one of these sections, and I know you're going to hate this color bar now, but it's really old, but here's your rainbow, no, what's it called? Jet color bar. Ugh. It's like despised these days, but when I was plotting this, it was all about jet. So apologies for the colorblind people, of which I'm also one of those, but here's the jet color bar. And this is just one of these gliders in the subantarctic, deployed for several months. I'm sorry I don't have time here, but I know that this is September and this is about mid-December, but it carries on till March. So we're only looking at early spring to late spring, and this is what the surface mixed layer really looks like in the ocean, in the Southern Ocean. It's changing temperature very rapidly. Here we've got a scale of what it takes to do in a day. That's 1 day. So in a week, we can go from pretty medium sort of mixed layers, 100 meters, to 300 and something meters deep. And then a day later, we're back at 100 meters or 60 meters. And we're changing this temperature quite considerably. So something is going on there. There's didn't really expect this when we deployed the gliders. We hoped we would see something like this, but we didn't know we would. And so there is a lot of lateral variability here, mesoscale and submesoscale interactions that cause all these gradients in the ocean. I mean, there's also one-dimensional processes, but you cannot get that from only one-dimensional processes of changes in buoyancy. And then we have a plot here of n squared. So that's that frequency I was talking about that I showed you in the lab experiment. We can get that because we have measured density, and you get these patches of high stratification, and then it disappears, and then stratification starts forming on the surface. We're like, oh wow, that's really interesting. But also, at this time of year, there's very little net solar radiation. So we have very little heat gain here to account for buoyancy being driven by solar radiation. So something is causing stratification to increase here that's not necessarily solar radiation. Keep that in mind, because that'll come back later or probably tomorrow. And then it deepens again, and things change. The biology also gets very excited. These gliders carry these ecopacks and can measure fluorescence from as a proxy for chlorophyll A. And so we can see that during these stratification events, the primary production increases. We get these pulses of primary production. And then only later is the seasonal summer bloom really setting in. But something is happening earlier on in spring that's really changing the phytoplankton before you would expect the spring bloom to happen. And if we look at the integrated n squared over the mixed layer, or at least over the 100 meters, the first 100 meters, we can see increases in stratification that are happening pretty much at the end of winter. So it's still very cold, but the ocean is still managing to stratify somehow. Okay, this is a view of the mixed layer that we predicted from products available while the gliders were in the water. So here we have a monthly EN3 product. Now you use EN4 is available, and you know it's pretty much better resolution. But back in 2012, we had EN3. We have the CFSR reanalysis product, which is weekly. So you see the mixed layer changing over time. And then you put the gliders on top of that, and you kind of get a different view. This is the mixed layer that's occurring from the gliders. So there is a lot of information that we do not get from reanalysis products because we're not able to resolve them. Here's Table Mountain, for the South Africans in the crowd. If anyone's been in Cape Town, because maybe you got on the Polarstern there or something, if you're at the base of Table Mountain and you kind of look up, you're looking at about a height gain of 500 meters. We're not talking from sea level, we're talking about like at the cable car station. It's really quite a big mountain right by the city. And now you can imagine that the mixed layer is changing kind of in this height of Table Mountain on timescales of a day or two, or maybe at a spatial scale of 20 kilometers or 50 kilometers. So it's quite dramatic. Something is missing. Okay, and what about, this is for the SEAL people in the crowd. How many of you are working with SEAL data or SEALs directly? Yeah, so it's definitely got you guys involved here. So these wonderful SEAL tags, they also give us a lot of information what's happening under sea ice. I mean, what is going on in terms of the mixed layer under sea ice. And here you can see some of these seals leaving from Bouvet Island, the most inhospitable place in the world. It's just cliffs and seal poo and mud. And these incredibly brave people go and tag seals there. Some people in France, but a lot of people at NPI in Norway. And they tag these seals, and then those beautiful elephant seals go and find food in the Antarctic sea ice, in the Weddell Sea, and collect this really incredible data under sea ice, also at relatively high resolution. Several kilometers between dives, and several hours between dives, which means they're kind of like a biological glider for us, flying around and collecting data under sea ice. And they can really tell us also a lot of information. So this is just the mixed layer again. Now we have sea ice concentrations that are nearly 100% here. I mean, it's pretty much covered in sea ice. And the mixed layer is still changing a lot. You would expect, theoretically, the sea ice lid would come on there. We would shut off the surface buoyancy, the one-dimensional buoyancy and wind stresses. So, the mixed layer shouldn't vary very much. But the seals really show us that the mixed layer is varying under the sea ice quite a lot. And this is the perfect advertisement for Channing's poster. So go and check out Channing's poster, because he'll tell us a lot more about what's going on in the seal data, especially in terms of submesoscale fluxes. All right, 20 minutes left or so. All right, so the mixed layers can essentially, in a very simplified view, be seen as a battle between mixing processes like shear-driven mixing, because there's shear in the water column as we have these Ekman spirals and the wind stress, and a trade-off then with buoyancy. And here I'm mostly talking about buoyancy gain. So warming or precipitation or melt from sea ice. And we can actually express this as a non-dimensional quantity called this Richardson number, which is looking essentially at this ratio between the buoyancy frequency, which I explained before, n squared, and the shear in the water column. Now, we don't really have many profiles of velocity through the water column, but when you do, you're able to look at how the velocity in the upper ocean all the way down to the bottom might change as a function of depth. And if you have that, you can actually quantify the Richardson number. So a good old ADCP on your CTD rosette would be wonderful to quantify what might be the Richardson number. And if the Richardson number is falling to something below about a quarter, we just generically here, we term this as an environment that's prone to rigorous mixing. The shear term is much bigger than stratification, so it's outdoing stratification and overcoming it and deepening the mixed layer, and it's a very unstable environment. And when the Richardson number is large, let's say over 1, turbulent mixing is suppressed. So stratification is winning in this environment and shutting down the ability for the unstratified environment for turbulent mixing to occur. So turbulence is slowing down or shutting off completely. And then there are these shear instabilities, and I'll only show you one example. So the shear is, of course, we have a change in velocity with depth. So something, where that change occurs, something's got to give, and instability is going to form. And the one favorite one I like to show here is the Kelvin-Helmholtz instability. And many of you will know a Kelvin-Helmholtz instability because you see it in the atmosphere a lot. And here you can just see a very generic view of it. You've got a change in the velocity. Here we're kind of looking in the lateral scale, but you could see this as the vertical. You've got higher velocities on one side of a front or a patch of water than on the other, and instability forms. It starts to become very unstable, and it actually mixes out and eventually becomes turbulent dissipation mixing in the surface mix layer or somewhere in the water column. Right, and another video. So here is just a very cool animation of Kelvin-Helmholtz instabilities in the laboratory. So this person was, couldn't be me. It's exceptionally patient. I think she like tilts these. I should pause here to explain. She tilts. First of all, she fills this thing vertically. So we have less buoyant water on the top, lighter water on the top of the tank. I think it's the clear one. Yes, it has to be in this diagram. We have the less buoyant water here that wants to ride over and stay on top of the heavier, dense water, which is this colored water, the blue one. And it's all vertical and all stable. It's stably stratified. It's a stable environment. And she starts to tilt it like a degree every 5 minutes or something. So you can think of how long it takes from her to get to 90 degrees. That's why, she's got a lot of patience. Thanks to her for making the animation. And now she's got it in a sort of near horizontal plane. And what she'll do next is she's going to just tip it down back quickly to 45 degrees or something. There we go. She's like, okay, it's time to get going, guys. Had enough of this boring stuff. Now you're actually generating a flow as the two different buoyancy parcels of water are overlying each other. One is starting to flow up, and the other one's flowing down to become neutrally buoyant. And as that's happening, it's creating a Kelvin-Helmholtz instability, which is then entirely mixing all the nicely colored water, stratified water, into one color. And this is a typical example of a good Kelvin-Helmholtz instability. And this is occurring in the ocean too. And you see them in the atmosphere with these beautiful clouds that create these horse heads. And these are the beginnings of these Kelvin-Helmholtz instabilities that are also mixing in the atmosphere. And you should Google it because the music to this is the best. I don't know why I don't have the speaker, but the music is top class. So try it out, super cheesy. Okay, now the last thing I'll cover. The last thing I'll cover is, just missed it. She had like 2 colors there. Ooh, it's getting really exciting. Anyway, sorry, you have to do that yourself on Google. So the last thing I wanted to cover is, we talk a lot about the mixed layer depth. But the mixed layer depth is an time-integrated result of a whole bunch of processes that are occurring in the mixed layer. We measure a threshold as a change in density somewhere in the water profile, and then we're like, oh, that's the mixed layer depth. And that represents a whole bunch of processes that have happened sometime in the past, days to minutes, that allow us to say this is the mixed layer. But the mixed layer is not actually the active mixing layer. And those are two very actually distinguishable things. And that's the one thing I wanted to bring up because it's relatively new in our understanding is how important it is to understand the mixing layer, the layer that's actively overturning and is turbulent, versus the mixed layer, which is already mixed and is the time-integrated process of all the mixing, active mixing that happened yesterday or 2 minutes ago. And this is another way to introduce instrumentation into the talk. And here we have Brian Ward's ASIP profiler, this very tall thing. It's called an air-sea interaction profiler. The South African just put a beanie on. I mean, I'm from Sweden, I was sitting next to Naomi. She's like, aren't you cold? I was like, I'm so warm. It's so nice and warm. And I see the South Africans starting to put jackets on. Like, this is lovely weather. Sorry. Anyway, this is a Brian Ward's ASIP profiler. It's air-sea interaction profiler. It's quite a beast. It's sitting here on the deck of the ship. And the old version, now he's got ASIP 2, but this is ASIP 1, that we try to deploy in SOCHIC in the Southern Ocean project with not much success, but we can talk about that over several beers. This one has propellers, so it's deployed, and then it propels itself to about 100 meters depth, and then it stops propelling, and it's positively buoyant, and it wants to come to the surface, and it rises very nice at a steady depth through the water column, several centimeters a second, until it gets to the very surface interface, the skin layer of the ocean, and it measures during that time high resolution, high frequency temperature and salinity. But crucially, it also measures shear. It measures the micro shear that's occurring. So it's talking about the millimeter scale or micrometer scale turbulence that's active in the water column, how active the little overturning cells are in the ocean using these shear probes. Where are they? Here. No, here. These are the various shear probes that are very intricately measuring the active mixing, the microstructure turbulence. Then we have an antenna to send us data, and we have a whole bunch of other sensors which you don't really have to worry about. Now, one of his PhD students, Valentina Winter, had done some very nice work at deploying these ASIPs on various cruises. So we have like 4 deployments here. And you can see that the ASIP, each one of the ASIP profiles is shown here as a measure of shear, active mixing. Have I got it? Yeah, I do have that right. To about 60 meters depth. And what she's plotted here is because she's also measured temperature and salinity, she can measure the mixed layer depth, and that's the black line. So the black line is what we would measure if we only had, the CTD going up and down. And then she's also plotted as a threshold what is the mixing layer, the XLD. We call this XLD. And you can see the yellow lines here are the XLD. So that is the active mixing layer. And obviously what should stand out to you is that they're really different. Like I'm talking about like sometimes 20, 30 meters different. So the active mixing environment of the upper ocean is often very different to what the mixed layer depth is. And that's because the mixed layer depth requires some time for buoyancy to grow in it, for it to actually shoal, for temperature and salinity to adjust and either shoal up in the mixed layer or actually even deepen further. Now we can see the same thing in the Southern Ocean, and this is a really wonderful piece of work that was led by Sarah Nicholson. So we deployed here several years ago the glider, and here the Slocum glider is now carrying that same shear probes like the ASIP on the nose here. So we can measure the microscale mixing from the glider, and we told the glider, okay, go north and south in this subpolar part of the Southern Ocean here. We're at the highest wind speeds part of the Southern Ocean. And then if that wasn't enough, well, then we put a wave glider on top of it to measure the other fluxes associated with it. But let's have a look first at the glider data. So we have wind speed that's measured by the wave glider on top. You remember I showed you the wave glider earlier. It is measuring the wind speed. There's these storms rolling through, and the surface stresses are increased significantly. And then we show the dissipation data, the active mixing in the surface layer of the ocean, so down to 200 meters. And what you can see is these pulses of active overturns, tiny microstructure overturns, mixing, extending sometimes to 200 meters and then sometimes shoaling and not being very actively mixed, back to 50 meters. And these active mixing events correlate very well with the surface wind stress. So the winds are providing this shear mixing terms that are deepening the mixing depth. So this is the XLD in the black line. Now she also plotted the mix layer depth as these other lines. So I think it's the dashed line here. And you can see that, whoa, the XLD and the mix layer are really not very well correlated here. They're very different. Why is that important? Okay, well, here we have salinity. Now we take the wave glider. Here's a wave glider. This is not the wave glider we're using. I think this is some military one because it's black. So it's probably some stealth wave glider. But this is what the wave glider is experiencing, for now 6 months. It's out there measuring PCO2, the gradient of CO2 between the atmosphere and the ocean, to look at how much CO2 is moving between the atmosphere and the ocean, PCO2 flux, and many other variables, temperature, salinity, blah, blah, wind speed. And then we can add the CO2 data, the actual CO2 flux between the atmosphere and the ocean. And what it shows, the bottom line message is this is important because these mixing events are able to tap into this high carbon, high DIC layers of water, circumpolar deep water, that have very high carbon, bring that high DIC water into the surface mix layer, which ultimately leads to a net CO2 flux from the ocean back to the atmosphere. So now the ocean is a provider of CO2 to the atmosphere. So without this fine scale view, we wouldn't really have known that this part of the Southern Ocean is actually a supply of carbon to the atmosphere. There's also been some wonderful work done actually with the SOCOM array by Alison Gray, who also showed that actually the subpolar, high wind stress parts of the Southern Ocean also have a high CO2 supply to the atmosphere. But with this fine scale view, we can really tell that what's actually happening there is that this active mixing is tapping into this high DIC water at depth and providing carbon to the upper ocean and then fluxing out to the atmosphere. Okay, all right, and then back to where we started, the climate models. What do we need to do? Well, the very short answer, we need to take a lot more observations at the fine scale. Here's a typical image from the proposal for SOCHIC of what we hoped to do and what we didn't really do. But we did a lot. We did a lot. So we tried to get there, but of course this is the perfect plan. We have these incredibly high, ultra-high resolution numerical simulations now, which are able to resolve the mix layer and the submesoscale circulations that occur in here. I'm going to talk about that a bit more tomorrow. And then we have these new, incredible satellite missions. And maybe you've heard of SWAT. That's up there now for a year. We've got PACE, which is looking at the ocean color, which is very, very new and very exciting. And all of these bits of information we need to provide a more understanding about the fine-scale ocean and its role in climate, so we can feed that back into the climate models to reduce the uncertainty of those models when we're looking 100 years from now. And I'll try and show some examples tomorrow of how that's working. And yeah, I'll leave it there. Tomorrow we'll get to SWAT and the fine scale. So I'll stop there for today, and tomorrow we continue with the submesoscale.